Our speaker today is Dr. Mike Aust, who is a faculty member at the Virginia Tech University. And Mike, I'm going to turn it over to you. Thank you.
Okay, thanks a lot. I appreciate all y'all joining us this afternoon. A little bit about the background for the presentation today. Several months ago, I was approached and asked if I'd mind putting on a webinar talking more about the research side of forestry BMPs. And what I'm going to try to do is to go through the rationale behind it, but also talk a fair amount about some actual results for some fairly recent studies. I'm primarily concentrating on studies that we've done here at Virginia Tech today, not because there's not a lot of good work done a lot of other places, but simply because these are the studies that I'm most familiar with, and I think they cover a range of topics that I hope will be of interest to y'all today. Now if I can find, there's the advance button. Some of y'all have probably participated in this series of webinars. There have been two prior to this. Jim Bowe started off the series with a talk on just general watershed hydrology, and then Graham Lockaby had one that was looking at forest land use, forest landscapes, and the effect that had on water quality. Graham was going more into the nutrient side of things than I will today, but Graham said he had a fair number of questions about BMPs, and hopefully some of those people that had questions about that have joined us again today. Now what I'm going to do today is basically talk a little bit about the legislation behind the forestry BMPs, and I realize that some of you, this is probably old hat, but we've got a range of different people and range of different backgrounds in here. I'm also going to go over just some general BMP considerations and then go into the research results and some potential applications of it. I guess the first thing is just to make sure we're all on the same page regarding what are forestry BMPs, or Forestry Best Management Practices. You know, it was really not until the Federal Water Pollution Control Act of 1972 that this terminology was really fairly widely used, and because of the federal legislation, it's worked its way into our terminology. Sometimes I think we probably should have called it something besides best, because ever since we've called them best management practices, we've continued to improve them. So if they were the best to begin with, well, they're even better now, I guess. Regardless, for most states define the primary goal of forestry BMPs as being some type of method, measure, some type of practice that you're using in order to either maintain or protect water quality, primarily from forestry, from the forestry perspective, from non-point source pollutants. The main one is sediment. That's the one that we focus on. They also protect the water quality, the streams, from increases in temperature due to thermal pollution, also chemicals, organic pollutants, a lot of different things. But sediment is the big one that we focus on. That is typically considered to be the most important non-point source pollutant in the U.S. Now, sometimes states will also have secondary goals for their forestry BMPs. You know, and all of these are tied together, and it's a pretty reasonable thing. But for example, site productivity as a secondary goal. Well, if you minimize erosion on a site, well, you're going to help maintain site productivity. So that makes a lot of sense. In a lot of instances, since we are working down near the stream, if we're leaving riparian areas, if we're leaving buffer strips, streamside management zones, this is going to have an influence on wildlife habitat. Also on wetlands, you know, because again, we are crossing streams very often, and we're in near proximity to the wetlands. And some states even have best management practices for around cemeteries and old house sites and things like that also. But that's not the focus of today's talk. Now, if we take a look at these two slides, it's pretty easy to see why BMPs can be so important. If you look at the upper slide, what we're looking at is we have a forest road, and there's a ditch on this particular forest road, and that particular ditch has some problems, and that ditch is generating a lot of sediment. Well, in this particular case, we've got a streamside management zone that was the best management practice. And that streamside management zone is doing a pretty good job of trapping that sediment. I hope all of y'all can see the sediment that is being trapped by it in this particular instance. Another example of where we use BMPs in many instances would be on roads and skid trails. If you take a look at the lower slide there, you can see a skidder coming down a very long skid trail. It was about an 800-foot long skid trail on about a 35% slope. Desperately in need of some water control structures and some closure measures once they're done with this. Now, in this particular case, I'd like to emphasize this, because this is a good example of where pre-harvest planning might have been a BMP that we could have used to improve the skid trail, before we had to deal with the problem in the end. And the streamside management zone is a good example of a BMP that actually is helping us to prevent a water quality problem that was due to another situation where perhaps additional BMPs might have been used. So I'd like you to keep that in mind, because SMZs are a good way of dealing with a problem that might occur, and pre-harvest planning is a good method of dealing with it ahead of time. Some people consider those to be two of the most important BMPs. And again, they're all important. Okay, now, the legislation. As I said before, the primary legislation that has basically led to a lot of the BMP programs across the country was the Federal Water Pollution Control Act of 1972 and the subsequent amendments, and this is generally referred to as the Clean Water Act. That's what most people refer to it as. Now, what we're typically dealing with are the portion of the Clean Water Act that is dealing with non-point source pollution. Not point source pollution, but non-point source pollution, where it's coming from across the landscape, where the pollution is coming from activities like construction in an urban area, or from silvicultural activities, agricultural activities, perhaps mining, these types of activities. Point here is that what we're dealing with all over the United States is very often generated out of Washington, D.C. So, if you take a look at the lower slide there, where we're looking at a cypress tupelo swamp, well, even as remote as that area is, the BMPs in that particular area are very often being driven out of Washington, D.C. in their efforts through the states. Now, there's also another term that we need to discuss, and that is silvicultural exemptions. Now, silvicultural exemptions really aren't truly exemptions. Silvicultural exemptions really are a blanket permit. They're a general permit. Basically, silvicultural exemptions mean that we do not have to get a permit when we're dealing with, particularly around forested wetlands, around streams, these types of things. We don't have to get a permit, as long as we follow certain conditions. It has to be a normal silvicultural operation. If you take a look at that deck and the upper slide there, again, clearly a normal silvicultural operation. That was a pretty hot deck, the merchandising, a lot of wood, but normal silvicultural operation. Has to be an ongoing operation. This is why a management plan is always a good idea on site, so you can prove that it is ongoing. They have to follow the federal BMPs, and the state BMPs are somewhat implied. We'll talk about the two sets of federal BMPs later. You can't introduce toxins to the stream, and you can't significantly alter the hydrology of the site. And that has been something that's come up under several different lawsuits over time. Now, in some particular instances, we may have to get a permit, and by we, I mean the forestry community. A good example would be here in the state of Virginia, if we're dealing with permanent stream crossings for watersheds that are larger than 3,000 acres, then we may have to get a permit to build a stream crossing such as the one we're looking at there. Other states have different requirements, but that's just an example of where the silvicultural exemption might disappear for a particular activity. Now, for the federal BMPs, I said there's two sets, and basically there are 15 federal BMPs, and this is for private land that I'm talking about now, that are primarily related to roads and wetland areas where you're dealing with stream crossings, that type of thing. Most of them are pretty common sense, and you can get a list of those, take a look at them. And the other one is typically looking at where you're going into some relatively wet areas and establishing pine plantations. Those are the two general sets that we have. Now, we also have a lot of federal BMPs for federal land. I just reviewed a set of federal BMPs for federal land just last spring, and it was, I believe it was 900 and some pages long. They're pretty impressive as far as the length of that. Now, for most of you that signed up today, just kind of quickly scanning where you were from, most of you, I think, are going to be dealing with the voluntary state BMP programs. These are primarily in the southeastern United States, the central United States. Within these programs, the states use different techniques to monitor the best management practices and to come up with the compliance rates. These may also be linked to other industry standards. The Sustainable Forestry Initiative also has some level of BMP compliance associated with it. That's just an example of how that might be linked in. Some states also have additional legislation that may allow them to potentially fine if they identify a particular problem with water quality. But in general, in those regions, the states have voluntary BMP programs. And in the slide here, we've got one of the state foresters talking to a group here about that BMP program. And all of these, again, there's just a range of ways that these are implemented. Some of them try to inspect every site that's harvested. Some of them do subsampling. Some do it on the ground. Some do it in the air. There's a lot of different mechanisms for this. And we also have some regulatory state programs, and I'm assuming that a smaller set of you today are coming from states that have regulatory programs. And these are primarily located in the Northeast and the Pacific Northwest. There are exceptions to the rule, but that's in general where they're found. And many times these regulatory programs are in fact some type of Forest Practices Act. There's an example of Oregon's here on the right. Don't need to go through all that verbiage. It's just an example of a Forest Practice Act, the preamble to the Forest Practice Act. And the other thing about these is that very often these will involve multiple agencies and disciplines. They may or may not necessarily be linked to the primary forestry agency within that particular state. And then we have some BMP programs that are really kind of multi-state in nature. A good example of that would be the Chesapeake Bay Agreement between several states surrounding the Chesapeake Bay. And basically under this, the states in that region agree to implement stricter BMPs in that Chesapeake Bay area. And you can see an example of Virginia's there on the right, where basically you have to have a larger SMZ if you are in, and it's a mandatory SMZ, but it's also larger if you're in a Chesapeake Bay county. But that's an example of a multi-state BMP program. A couple of other examples: the Southern Group of State Foresters has an annual meeting where they discuss BMP compliance, BMP inspections, various problems that they have in that region, and the National Association of State Foresters also does this. We've got a project going on here right now where we are working with the National Association of State Foresters to survey all of the membership and find out what the current compliance levels are and how BMPs are being implemented in the various states and territories. Now, another reason that this is of interest, particular interest, is because of some of the recent court cases dealing with forestry BMPs. Most of you are probably aware of the court case that went on in the Ninth Circuit Court of Appeals. It goes under several different names, but the NEDC versus Brown is one of those. Decker is another one. But basically what this case was about was whether some ditched forest roads, particularly at stream crossings, should be considered as point sources of pollution as opposed to non-point sources of pollution. And if this had happened, they would have required a permit for the stream crossings. Okay, and that actually went through. This went all the way to the Supreme Court, and basically the Supreme Court is allowing the EPA to develop the policy, use basically their existing policy on this. So it did not change it to point sources of pollution. Now, what this has done, though, is it has placed additional focus on both ditched roads and on stream crossings, and we can probably expect to see additional focus on those types of areas in the very near future. You know, and again, this would be an example in the upper slide of a ditched road leading down to a stream crossing, and then we have below that just stream crossing. Both of these might be instances where you might need to, under the Ninth Circuit Court ruling, where you might have needed to go through the permit process. We've avoided that for now, but you know, we're going to see continued focus on that. Okay, now starting to get into the BMPs. If you take a look at that slide, look at those BMP manuals, they all have different covers, but when you start opening them up, they all deal with basically the same things. They all deal with pre-harvest planting. They all deal with harvesting. They all deal with roads, decks, skid trails, stream crossings. All of them have a section on site preparation. They all deal with fertilization. And when I say site preparation, I mean both chemical, mechanical, fire, and they all have a section on streamside management zones. Now, after that, they may diverge and have, you know, an area on wetlands, depending on where you are. They may not, but they will all tend to have these particular components. Now, I guess the first thing we will talk about are for the in-woods transport, and you know, whether you're talking about the permanent forest roads, whether you're talking about temporary forest roads, roads tend to be a major consideration for BMPs. And then we've got the decks or the staging areas. Again, these all BMP manuals are going to deal with that. And then we actually start to get to the in-woods transport, where we're dealing with bladed skid trails or overland skidding. Also, stream crossings are of particular importance, because stream crossings are the areas where several projects have shown that if you are going to introduce sediment into the stream, this may be where it happens. And interestingly enough, most of the BMP manuals deal less with the harvest area than these other considerations, because it's really the roads, the decks, the skid trails, and the stream crossings that tend to cause the most problems. So they get the most emphasis in the BMP manuals. And then the last zone of defense between all of these other things in the stream side management zone. These do go by different names in different places. They're sometimes referred to as riparian buffers, buffer strips, a lot of different names. Another general area that BMPs tend to focus on are erosion and water control. You know, if we can prevent erosion, we can keep the sediment from getting into the creek. If we can control the quantity of water, if we can control the velocity of the water, if we can control where the water is going, we can also minimize the amount of erosion that makes its way into the creek. One thing that's very important is where you locate your operations. You know, trying not to put decks near streams, trying not to put roads near streams. If you do have to cross, trying to get across as quickly as possible. Minimizing bare soil areas. If you take a look at that upper slide there, you can see that this is a pretty nice road. That's a pretty nice forest road where we've got water control structures in place. We've got some riprap around the culvert. We've got straw on the road. There's some gravel on the road. It's got a low grade to it. That's pretty doggone nice road that we see there. Okay, another important factor is to minimize the area of skid trails and roads, because that will maintain infiltration rates on the site. When we start compacting large areas, we can start seeing more runoff. If we see more runoff, well, water runs downhill and dirt goes with it. The more water you have running off, the more dirt you could potentially move around. Another important thing is to try to revegetate the site as quickly as you can. We want to restore the evapotranspiration as quickly as we can on a site, because again, that will minimize the amount of water that's going to run off from it. We want to, for our roads, our skid trails, our stream crossings, try to keep our slopes, you know, below 10% when we can. 10% is that point where sediment really starts to increase. We also want to minimize the distances on these slopes. Okay, I've got a question here that says, how are typical erosion control forestry, oh, it's moving here, my question's moving too fast. How are typical erosion control forestry BMPs calibrated for a 1 to 10 year storm, a 1 to 25 year, a 1 to 50 year interval? In the North Carolina mountains, we're seeing some typical BMPs being used, but blown out from unusually heavy recurring rains this year. How would we calibrate our BMPs for the future? Well, that's a really broad question, and they're calibrated for different rainfall events. Typically, the way you'll see it is for permanent structures versus temporary structures. Culverts are a good example where in Virginia, there are at least 3 different ways that we calibrate how large of a culvert that we might need for water control. And again, I can't say that one size fits all. But if you do see that your standard BMP, you're having trouble with it blowing out, I would say this would be a good time to look and see how unusual was that rainfall event. And then if it really wasn't that unusual, well, then that particular standard might need to be increased. You know, you might need to use a little bit larger culvert for that. I realize I'm giving a pretty vague answer to that question, but without actually seeing the situation, that's about the best I can do with it right now. Hopefully, if you have more on that, you can send me another question. Okay, coming back to the slide, we always want to try to minimize our contact with the stream, and we want to try to reduce water velocity and trap the sediment before it gets to the stream. Take a look at the center slide there. That's an important BMP that we see going on there. That's a skidder that's backhauling Slash, and they're going to dump that on their skid trail. This is a really good BMP, particularly for trying to close out skid trails at the end. And it can be a relatively low cost one. In the lower slide, we see a road here that's been seeded. One thing I really don't particularly care for on this particular road, I'm familiar with this road, is that it's so shaded. This road would be a better road if it were daylighted a little bit more, but in this particular case, that's really not an option, but it is well seeded. Okay, pre-harvest planning. Now, pre-harvest planning, I said before, can be one of the most important BMPs. This is typically where we consider where we're going to put our roads, where we're going to put our decks, where we're going to locate skid trails, and this may be where we actually identify stream crossings and identify the streamside management zones. Here in Virginia, one of the things that they use as evidence of pre-harvest planning is whether or not the SMZ was actually painted or flagged ahead of time. You can come back after the harvest and see that it was painted. And that's pretty good evidence that pre-harvest planning was part of the operation. Now, Bob Schaefer and Greg Mead did a study several years ago now, but I think this is a study that really shows the importance of pre-harvest planning. What they did in this study was they took two groups of loggers, and one of them received about a day of BMP training. They had an in-field workshop, and then there was another group of loggers that were non-trained. Okay, now what they did was they collected data from the Virginia Department of Forestry inspections that were done on all these sites. They collected the logger data every week, and they called the landowners that the loggers were working on. And they did this for an 8-month period for the group that had training and the group that didn't have training. And the trained group almost immediately reported that two of the big benefits that they got out of the training was better use of topo maps for planning their decks, their stream crossings, these types of things. And they also reported that they spent more time planning stream crossings, like the one you see in the upper slide there. So just those two things tell you that they got some benefit out of this training pretty quickly. All right, now at the end of the study, both of the groups overall performed very well, but the trained group clearly had an advantage here. If you look at the BMP inspections that were done by the Department of Forestry, it was 90% compliance for the trained group, 80% compliance, 86% for the non-trained. Not a big difference, but an increase. Landowner satisfaction increased with the trained group, and the weather-related time losses decreased for the trained group. So, for the BMP inspections, we could say that the state won. It was improved for the state. Landowner satisfaction, so the landowner won, and then the logger also won. The logger actually lost, during that period of time, almost 7 working days less time. That's a pretty big difference. So this training helped. Okay, now Charlie Bland and I reviewed about 50 research papers a few years ago now looking at the effect of harvesting on water quality, and basically overall, if you take roads and skid trails out of the equation, and we're just talking about harvesting, harvesting has really a minimal effect on water quality. Okay, now that has some caveats with it. That is assuming that the appropriate BMPs were applied, the area was allowed to revegetate, you got vegetation back on it as soon as you could, and that the roads and skid trails were retired. Where we didn't see that was where we saw the problems. For example, if you take a look at the upper slide versus the lower slide, here we have 2 stream crossings. They're within about, probably 10 miles of each, probably 15 miles of each other. Both of them are crossing through the SMZ. The upper slide, though, if you look at it, has a gentle slope. It has nice water control structures. The area has been seeded and mulched. The area had gravel on it. Very nice job. If you take a look at the lower slide, we see that the road is about a 17% slope coming down on one side and about a 19% slope on the other. The water control structures are failing. Sediment is being delivered to this particular stream. The road itself is rutting out. Again, clearly one where we need to come back in and do something pretty drastic on this one. Okay, but again, that's the caveat. If we can have the roads and the skid and the stream crossings, but we have to be careful with them. They can make a mess in a hurry. Reinvestor and Ed Christopher did a project where they used the universal soil loss equation to estimate erosion on almost 60 harvested sites across the mountains, the Piedmont, and the coastal plain. Okay, and what they found was that the harvest areas had fairly low erosion rates after closure. The areas where we continued to have problems were with the roads and the skid trails, even after the harvest closure. Now, the interesting thing with this is that some of these jobs had been completely satisfactorily closed. The problem is that they were being reopened by four-wheeler traffic. That was really probably one of the most important findings of their study, that was even when we closed the road outright, some of the hunt clubs and things like that were coming in and reopening those areas and basically wiping out the BMPs. So that's something that we have to deal with. Sometimes people ask, what about alternative harvest systems? Could we use something like cables, and just get away from the roads, get away from the skid trails? Well, we're fortunate. Here a few years ago, there was a landowner in the mountains here in Virginia that had 3 sites where they were going to use cable yarding and they were going to use bladed skid trails, okay, on the same site. So we had 3 sites where they were using both of them side by side. So we could go in and look at erosion on those sites, estimate the erosion by different categories across the site. I won't go into all the details, but in this particular case, the cable did produce slightly lower erosion than the conventional skidding, the bladed skid trails. The cable produced about 1.7 tons per acre per year of sediment versus the skidder 1.9. Those are both pretty low. Now, the reason though that the cable was not better than that was because they were yarding. If you see in the upper slide there, you can see where they had the yarder set up, and they had a skid trail where they were pulling the logs from the yarder to where they were loading them at the deck, and that had about a 25% slope. So in this particular case, we were using a cable yarding system, but the roads were even worse than on the conventional system, and that's why this didn't look better than it did. We saw this on all 3 sites, that the roads from the yarder to the deck were, well, they were not great roads. Another alternative harvest system is helicopter, and this was a study that was done down in Alabama. It's been going on for 24 years now, but what I'm going to show you now is from age 23, where on the same site we had 9 areas where we harvested with a helicopter and 9 with a skidder. We also had some other treatments, but that's what I'm going to talk about primarily today. And what we saw on this particular site was the differences were not as large as what we thought they would be. And also, in this particular case, at age 23, the skidder was actually, the upper box there is looking at the total number of stems by treatment. If we just look at Tupelo, which was a desired species on that site, the skidder was actually better than the helicopter. And in this particular case, the total number of stems was actually slightly better than the helicopter. Okay, now if we look at the lower box, we can also see for the helicopter and skidder, we're looking at the volume. We're looking at the volume there. Okay, and the skidder was higher, and again, these are metric tons we're looking at, but the skidder was higher than the helicopter. This was not what we originally thought would happen on this site. This is why, we can't just have blanket BMPs for all situations. We need to have professional involvement with this. Now, the reason that we found this is because of some of these things. The skidder actually created microtopography. This was a really wet site. I mean, this was a cypress tupelo site, and the skidder actually, when it created the ruts, it was actually almost like creating beds on this particular site. So it was creating pockets that were better drained, and we got some regeneration on those, but we also got roots growing up into those more elevated areas. Another very important thing on this site was that these had shrink swell soils, and these shrink swell soils recover much more rapidly. When they wet and dry, they shrink and swell, so compaction tends to be naturally negated that way. Another really important factor on this site was we had a lot of sediment being trapped. We had between 10 and 16 inches of sediment trapped on this site over a 23-year period. You know, that much sediment coming in is also going to offset the compaction. That, you know, you're bringing in non-compacted, nutrient-rich sediment. We also had very active crawdads on that particular site. They were cutting through some of these skid ruts. They were, the hydrology was recovering where we had puddled in the skid trails. The slash had a lot of carbon inputs that was buried by the sediment eventually. We found preferential root growth in that buried slash. We had a flood-tolerant species on that particular site, and we also had a species that regenerated well from coppice. Okay, I have a question here that is, where did that sediment come from? Well, this is on the Tensas River in Alabama, and that's got a really large watershed. You're looking at potentially that sediment could have come from all over the state of Alabama. It could have come from portions of Mississippi. It's even part of the Tennessee Tom waterway. So the source of the sediment is unknown. You know, this is overbank flooding. This was not being delivered from an upland source. Well, it's being delivered from an upland source. It was not being delivered by overland flow. It was being delivered by overbank flow. Okay, this was a study. Scott Barrett recently just did this, and he was looking at biomass harvesting. There's been a lot of interest in biomass harvesting and the BMPs that might be needed or not needed with biomass harvesting. So what Scott did was he went and found 20 sites, and well, he didn't actually find them. The Virginia Department of Forestry were auditing these sites, and he got a mix of 10 conventional and 10 biomass harvested sites. And he went across all of these sites and estimated the erosion potential from all the different operational categories, from the harvest area, from the decks, from the roads, from the skid trails, from the stream crossings. You get the idea. Okay? And basically didn't find any differences in sediment between these treatments. Now, what he did when he was going back looking at the audit information and doing a BMP inspection himself on these sites, what he found was that the biomass harvest did tend to be too aggressive in cutting the SMZs, and they left smaller SMZs, and sometimes they removed higher levels a basal area than is recommended from within the SMZ. But this isn't really a fault of biomass harvesting per se. That was an operator choice. You know, so what he concluded was that there wasn't enough slash being left on this site for use in BMPs. He didn't see any difference between those as far as use of slash as a best management practice, but he did conclude that the contractors needed to pay closer attention to the SMZs. Okay, I have another question that says, I'm in the hills, not used to this type of sedimentation. Well, in these large bottomland hardwood stands, that type of sedimentation is not really that unusual, but it would be unusual in the hills. Okay. Now moving along to roads and best management practices. Forest roads, really, we need them. You know, for many of our activities, they're absolutely vital. I mean, we can't get the timber out without roads. They typically enhance land values. But on the other hand, they're really expensive to build. They're really expensive to maintain. The BMPs are costly on them. And numerous studies have shown that roads can be a major source of sediment. And I think if you take a look at these two slides, you know, it's pretty obvious why roads can be a major source of sediment. They tend to have, or they can have, a lot of bare soil. They can have long, steep grades. They may not have adequate water control. And the BMPs, to fix the situation after the fact, tend to be pretty expensive. There's another view of that same road that we looked at earlier there in the lower slide. This particular one is kind of a poster child for me as far as, you know, not what we want to do. Now, A.J. Lang's a graduate student that is working on the relationship between sediment that is produced and the road class. And road classes are really a combination of the road standards. You know, how wide is the road, how steep is the road, how much gravel is on the road, is it ditched, is it outsloped, what type of water control is used, what type of stream crossings are used. But Class 1 roads are better roads, Class 4 roads are the not so good roads. And what we see is a pretty good relationship between the road standards and the sediment that's being produced. Now, what he's looking at is he's particularly focusing on stream crossings with this. The thing to keep in mind is that when you have a Class 4 road, you may be satisfied with a Class 4 road, but we might at that particular spot, at that stream crossing, choose to go more towards the standards of a Class 2 road or a Class 1 road. You know, so again, you might get a bigger bang for your buck by spending your effort at that stream crossing. Another issue is designed roads versus legacy roads. And Rob Feldt, he was a grad student a few years ago now. He's a BMP forester up in Maryland now, or he was the last I heard from him. He looked at roads in the Allegheny Plateau, or in the mountains, and in the Piedmont. You know, so what he was doing, he was working on company land, and he was evaluating roads. And typically, most people would think that the Piedmont has more gentle slopes. This would be the area where you might produce less sediment. The Allegheny Plateau has some very steep side slopes, mountainous, rugged terrain. You would think that it might produce more, but that is not what we found, because most of the roads that we were dealing with in the Piedmont tended to be these legacy roads. These were the roads that some of these roads probably go back even to the 1700s. I mean, they're old farm roads, they're old horse roads. And they were never really built in the right place. The road standards aren't as good. And the other thing is that these were legacy roads. There had not been an engineer involved. And they didn't tend to have as much gravel on them. You know, if you just contrast, these are kind of just very representative pictures of the roads from those two areas, the Piedmont on the top, the Allegheny Plateau on the mountain. You know, very different roads on these legacy roads. Sometimes the cases aren't that extreme, but legacy roads tend to be more of a problem for us. Here's an example. Chris Brown is doing some work looking at sediment contributions from some of these legacy roads. And what Chris, he broke these up into different categories, where he was looking at roads that had bare soil and they were in an open condition, bare roads that were in a forested condition, and then graveled roads that were forested, and then compared that to just mature forest. And you can see that where you had bare roads and you didn't have vegetation to uptake water on that site, some of those roads were producing 180 megagrams per hectare. You can basically cut that in half, and that's tons per acre. That'd be roughly 90 tons per acre per year. Big factors there were the road area, how long it was, and then the spacing between the water control structures, and then of course gravel. Problem with gravel is it's just very expensive. This was another project where Chris was doing another stream crossing evaluation. He looked at 3 stream crossings, and he had an approach on each side, so he had 6 approaches, and he used a rainfall simulator to simulate rainfall intensities. And he used 3 levels of BMPs on these approaches. He had one with no gravel, he had one where he graveled half of the approach, and then he had one where he graveled the entire approach. And this was what he found. Basically, the lowest level of BMP compliance, where you basically had bare soil, that contributed 7 times more sediment than graveling half of it. Okay, but then if you compared graveling the whole thing to graveling half of it, that produced 2 times more sediment. Okay. So the biggest bang for your buck there was to gravel half of the approach. 7 times more sediment is a lot of sediment for graveling half the approach. Had another student, Sally Dymond, that was looking at road area, and she was using a model from the West Coast, the distributed hydrology, vegetation, and soil model. Kind of a cumbersome model, but it allows you to look at the effects of roads on water yield. So we went down to Coweta because it's one of the few spots where they had enough data. This is a Forest Service hydrology lab down there. And Sally modeled different road densities. She looked at 6 different road densities, and she looked at 3 layouts for each of these, and then modeled the effect of road density on water yield, which would surely be related to sediment. And once you got past 2% of the area in a watershed that was roaded, we started having increased water yield. So the take-home message there is to try to minimize the area. Dave Passauer was looking at the effect of severe wet weather churning. This was down in South Carolina. These were some loblolly pine stands down there. Basically, he found that on the sites where they bedded it, you could offset the effect of even this severe churning like what we see here on the left. Now, this particular site has mixed clay mineralogy. We have that shrinking and swelling going on here. There's a similar study going on right now in Arkansas that seems to be indicating some longer-term problems around the deck areas. This is a study looking at bladed skid trail and the closure techniques that might work well for that. This was Charlie Wade for his graduate project, and he looked at, he put in all these bladed skid trails. He put in 30 bladed skid trails, and then 5 of them he put water bars only on, 5 of them he seeded, 5 of them he seeded and mulched, and then 5 he used hardwood slash, and 5 he used pine slash, and he monitored it for a year. And he weighed these sediments. Okay, and you can see the control produced about 61 tons per acre there. The seed produced about a quarter of that, and then the hardwood slash, the pine slash, and the mulch all produced less. Take-home message there is that those all 3 worked better. I just got a message here that my 5 minutes is up and we're starting to run out of time. I will just continue talking. I mean, feel free to leave or not. This is continuing along with that, looking at the effect of season on sediment, and we can see that through the course of the year that the control area continued to lose sediment. That was just water bars only. The others did not. We also looked at some of those models for modeling erosion. And the interesting thing here was that when we compared our actual value of sediment versus 3 commonly used models, USLE, Russell II, or WEP, what we see is that none of them worked perfectly in all cases compared to the actual, but they all predicted roughly the same trends. So again, these models are useful tools for comparing treatments, not necessarily predicting erosion, but comparing treatments. This was a similar study that was done by Clay Sawyers. He used the same 5 treatments that we were looking at before, but in this case he was looking at overland skidding as opposed to bladed skid trails. I've got a question here. Where can we find copies of the research referenced in this presentation? Probably the easiest thing for most of you to do would be to type in the names and then a keyword, I don't know, like skid trail closure. Most of them you could type in Aust, that'd be another word you could use with it. And then go to Google Scholar. Most of you, I hope, know where to find Google Scholar, and then do that search and it should pop right up. Okay. In the overland skidding study, we used the same treatments that we were talking about before, but we got different results. I mean, we followed the same trend as before, but the overland skidding produced about 1/4 of the sediment that the bladed skid trail. And this was even though the overland skidding was on 25% slopes, or up to 25% slope. The bladed skid trail was between 10 and 15. It was simply due to the amount of cover on these overland skid trails. So given a choice, go with overland skidding. But again, the pine, the hardwood, and the mulch all did a very good job of closing out those skid trails, better than the other treatments, which are typically considered to be more traditional. Again, what we see, particularly for the controls treatment, the water bars only, we see that spikes of sediment throughout a year when we monitored it. So basically the conclusions for the skid trail, and again the slides there, you're just looking at the 2 different treatments. The mulch and the slash were all good treatments. If you were doing this in a vendor's format, the slash could be expensive. If you were doing this just as haul back, it could be absolutely the cheapest treatment. Again, it just depends on the operation itself. If all things are equal though, the overland skid trail would be a better way to go where you could use it as opposed to the bladed skid trail. Scott McKee did a phone survey of about 70 loggers looking at stream crossing BMPs, the types of crossings they were using, and found pretty wide differences between regions. In the coastal plain, the loggers were using portable bridges, a very good option. Piedmont loggers were using a combination of those and culverts, and the mountain loggers were primarily using culverts. In many instances, the bridges could be better, but there's a lot of reasons why people may still choose to use culverts. But all of the loggers reported that they were spending a significant amount of money on stream crossings. This was a stream crossing study that we did where we looked at 24 stream crossings. We looked at bridges such as the one on the lower left. We looked at pole crossings where we put in a culvert and put poles across it. We put in traditional culvert crossings and we put in reinforced forbs. We also looked at this before the crossing was put in, during installation, during the harvest, and after it was closed out. And basically what the conclusion was there was that the stream crossing approach is really more important than the specific type of crossings. If you've got a bad approach, it doesn't matter what type of crossing you're using. Now, having said that, The permanent crossings tended to produce more sediment than the temporary roads. Part of that is just the sheer area of them. And in general, the bridges produce the least sediment, the culverts produce the most sediment. There's no way of getting around the fact that when you put in a culvert, you're pushing dirt in the creek, and it's hard to get around that. So if you have another option, you might want to consider it. This is a study that another student is doing on different types of crossings. He's looking at total suspended sediment above and below bridges, culverts, and a geoweb forward. And he's using 3 different levels of BMPs on those, and he's applying 3 different levels of rainfall. And so far what he's concluded is that the construction phase is producing more sediment on these crossings. He also has concluded the culvert is producing more sediment during the heavier rainfall simulations. This was a study that we did looking, Laura Ware did this study, looking at skid trail stream crossings and closure techniques. We used the same crossings that we talked about earlier, where we had slash versus mulch. We're putting down water bars combined with fescue, lime, fertilizer, straw mulch, and then the mulch and silt fence is the same as the mulch plus silt fence. And what she did was she collected daily samples. She had automated samplers, so she was doing this on 9 stream crossings every day. So she was collecting samples above and below the crossings. And this is a little bit difficult to look at, but she broke her results up into rainfall categories: low, medium, high, and maximum. And she definitely found significant differences between the low, the medium, and the high. And she arguably, depending on what p-value you want to use, the maximum differences there are awful close to being significant. But if you look at the score mean, and that's really what is important, in every instance, either the slash or the mulch worked better. The slash worked better or as well in all of the categories. The mulch worked well in 3 of the categories. In every instance, the mulch and the silt fence did not work as well. We also looked at the cost of this, and what we found was that the slash, and this was what they actually paid the contractor to put it out there, so this was operational crossing, $120 per crossing. The mulch was about $280, and the mulch and silt fence was $345. So there's about a 3-fold increase in cost. Now, the slash and the mulch treatments worked well, but you got a wide range of costs. The interesting thing to me here is that the most expensive treatment worked the poorest in this particular example. The reason for this is that silt fence has been shown in many instances to work well. But in this particular instance, the silt fence was put right on the stream bank, and they did a lot of disturbance when they were putting it in. So basically, when you had overbank flow, you had water flowing right down the silt fence. It was the way that it was put in. So in this particular case, just because it was more complex did not mean it was more effective. If the silt fence, if they had backed off a little bit from that, it could have worked. But in this particular case, both the slash and the mulch work well. Sometimes we forget about Firelines, and we had a graduate student that evaluated all but one of the wildfires in the mountains of Virginia for a particular year, and he basically estimated erosion on those skid trails using some of those models we were talking about earlier that aren't perfect but are good for comparing differences between different treatments. And basically what he found was that these things need to be rehabilitated just like skid trails need to be closed out. In some instances, these areas are not being closed out like they should, and the steep Firelines were producing up to 200 tons per acre per year of sediment. Bill Lakel did a study a few years ago looking at streamside management zones and how wide they need to be. He looked at SMZs that were 25 foot wide, 50 foot wide, 50 foot width thinning, and 100 foot wide. And he did this across 16 watersheds, and then he looked at sub-watersheds within those. Guest, I don't have a question here. I do have a comment though. I'm going to move along since it's not a question. In those 24 watersheds, and he used a lot of different techniques to come up with the erosion estimates, but basically what he found was that all of the widths worked really well for trapping sediment. Trapped between 97 and 86% of the sediment that was moving across that site in the SMZs. You know, it's the inverse of that 3 to 14 that you see there. Where he found problems, though, were where you had a problem with a failed road, you had a problem with the BMPs on a skid trail, or you had problems with a fire line, or where you had a stream crossing. These were where the SMZ failed. And this, again, is just the layout that he had there, where he had 100 foot, 50 foot, 50 foot with thin and 25 foot wide SMZ. And these were some of the ephemeral watersheds that he was dealing with, where he put silt fence above the fire line, below the fire line, and at the SMZ. And I'm showing you this design and the picture of these SMZs because we followed up with another study looking at the effect of these different SMZ widths on fertilizer movement. We went in and fertilized those sub-watersheds with those same widths of SMZs, and the conclusion there was that the 25-foot SMZ or the 50-foot SMZ width thinning seems to be too narrow for the fertilizer nutrients. Part of the problem with the thinned SMZs was the way they had the thinning corridors laid out. If the thinning corridors had been laid out a little differently, I don't think we would have had the same issue. A.J. Lang's doing a study where he's evaluating some problems with SMZs. This is similar to some work that Red Jackson's done down in Georgia, looking at where SMZs fail, why they fail. But he basically walked all the SMZs on 16 harvest sites. He looked at 20 harvest sites, but 4 of them didn't have any SMZs. Okay, but basically what causes the SMZs to fail where we've got these old agricultural gullies, and basically when you harvest a site, you've got more water running down these ag gullies and they're reopening. In some instances just due to activities with the harvest, but a high percentage were also due to problems with roads and skid trails, those types of things. So gully stabilization and minimizing the number of crossings would be 2 BMPs that could be really important there. Richie Christian, he's the graduate student that is doing a survey now for the 50 states and the 7 U.S. territories. It says there, but it should be 7 U.S. territories, looking at the current BMP policy. And he will be able to, at the end of this, probably to produce graphs like this one that we're looking at, where typically we see that the implementation rates for BMPs tend to be going up for most instances. We recently looked at that data, and oddly enough, some of the areas that did look like perhaps the trends were not as favorable. Y'all can probably guess it. They would be stream crossings. All right, I'll basically run over time here. I think I basically said what I wanted to, but basically we know that forestry BMPs can reduce sediment. We know that they can, okay? Where we have problems are where the BMPs aren't necessarily properly applied. Maybe we're not using enough BMPs, or we have some issue like the old gullies, previous land use history. The major things that it seems like most areas, most states need to focus on are, again, the roads, the skid trails, and the stream crossings. I mean, there's always other problems, but those tend to be the big ones. Okay, I'm going to come back now and look at a few of the comments. Well, I'm not sure. There was a general comment that 25 and 50 are too narrow for wildlife as well. Well, that may, we did not look at it from the wildlife perspective. We were specifically looking at it in terms of sediment and nutrients, primarily nitrogen and phosphorus. Okay, Rob, are you there?
Yes, I am.
I have run over by 11 minutes. I think we had a few more questions than I was expecting. I hope that was okay with everyone.
So folks, what I have done is I sent you out the link for the evaluation and quiz, which at the end of the webinar here. If you have signed up for continuing education credits, it'll prompt you for the quiz as well as the evaluation tool that we use, the survey. I do ask that you take the time to do that. Give it a minute here while it uploads on your browser, because there's over 80 of us here. It's trying to do it all at once. It'll take a second or two to do that. I'll also post it again here in the chat window for you. You can always copy that link and paste it in your browser or save it for later and come back and fill out the evaluation and the quiz. And with that, I'd like to thank everybody for participating today. And I'd like to thank Mike for taking the time and energy to put all this together for us. A lot of material to cover in a short period of time, and we appreciate that he's taken the time to try to do that. So thank you, Mike.
I was happy to do it.
And with that, the webinar is over. Thank you.
Bob?